All right. Good morning, everybody. Welcome back to Comp 2452. I hope that you're all doing okay today. I hope you had a good weekend. I don't know if it's just me, but like campus seems like it's really quiet the last while. It's getting to be that time of the term, I guess, but in some other ways, campus is getting less quiet. Yeah, I saw that this morning when I was walking here from my car. They're definitely back. They are definitely back here. Yeah, they're definitely back. There were also a couple sitting in front of the admin building when I was walking by, and they were just, sitting there eating grass as geese are wont to do. So yeah, welcome back. Like I said, I'm kind of conflicted because it means spring is coming, but it also means geese are back. There's one thing I wanted to bring to your attention before I start stuff about the test. So, I mean, one of the things that I think is reasonable for you to expect on the test is to like show how database stuff interacts with the programming language that you're using. We're using PG-Lite to do all the database stuff. And when we're working with PG-Lite here, one of the things that PG-Lite does, I think I've just opened 600 tabs with the same thing, and I don't know what's happening here with my web browser. One of the things that PG-Lite does when we call methods on it like query is that it returns this type results t. What I'm going to say to you about this is you don't need to know how results t is actually shaped. Like, that's not important to me. You can assume that if you do something like make a selection from an object or make a selection from a table, you can kind of just assume that the thing that the dot query method or the dot SQL method would return is going to be a JSON object that just has the column names as keys. So you don't have to worry about like how to parse out what the result structure is, but you can assume that you get something back from the database that looks like something you could reasonably work with. So by that I mean, like, you don't have to worry about knowing that affected rows is equal to 1 here. You could assume that you would get back, if you were to say select from test, select name from test, it would have a key of name and then a value of whatever the value actually is. Yeah.
What about providing a type of limiter term? That's a JSON object, like in the query, and then this weird.
Oh, like the angle bracket? Yeah, don't worry about that. The question was about putting the shape of the result into the angle brackets. Don't worry about that. Again, that's not something I'm actually concerned about. That's something that you'd kind of figure out with your actual. The thing that I kind of care about is that you can run queries and you get data back from those queries, and you can make transformations of the results that you get back from the queries. But the results that you can assume are going to be in the form of, like, it's just a JSON object, and you can just work directly with that JSON object. Are there any other questions about that before I just get back to stuff? Yeah.
You still want us to do things like expect we're getting some kind of results back into results.rows?
No, don't worry about that. So if there's more than one row, you can kind of just assume that it would be an array of JSON objects. So rather than just being one, sorry, that's gray on black and it's impossible to see. I hope that's easier to see now. You can assume that you'd get back an array, and the array would contain the same JSON objects that you'd get back if you were to just get one. If you do write out like rows dot or results dot rows, fine, whatever. All I'm really trying to say is you don't have to worry about memorizing the structure of that class, because I really don't care about that. Any other questions? Okay, all right, awesome. I'm going to close all these tabs I opened. Okay, we still have this cookie dragon. What can we buy here? We can buy like lots of everything here. We're getting close to being able to sacrifice 100 grammas, but I might have to leave that to the afternoon class at this point. Okay, we can sacrifice 100 grammas now. Okay, so we'll sacrifice 100 farms next time we're doing this. The achievement unlocked is just wrong because we've now sacrificed 100 grammas here. All right, so what I want you to be able to do by the end of today's lecture is I want to wrap up this state machine stuff. There are a couple of things that I want us to be able to make sure that we're including in the state machine that we've got a little bit to make it consistent with the C implementation of the state machine that we had. But this isn't really making any major transformations of the state machine that we drew out last class. This is really just adding a couple of extra concepts to make sure that we have something that's relatively complete for doing things like accepting valid email addresses and rejecting invalid email addresses. Once we're done with that, we're going to start moving on to taking a look at a basic AI or ML algorithm and data structure, and the structure that we're going to look at is called a Markov chain. We'll see this when we start looking at it, but if you squint at Markov chains and state machines, they look almost the same. They almost look like the same thing, but they behave differently. They do different things. I'll say this when we get to it, but where a state machine accepts input to move between states, a Markov chain generates output at each state. That's the major underlying fundamental difference between these two things. If you squint at them, they really just look very similar to each other. They're very, very similar to each other. Okay, so what I want to do with this state machine is just add a couple of small concepts so that we can make sure that we have something that matches what a C implementation would actually look like for this. So the first thing that I want to add is I want to add this symbol that really represents the end of a string so that we can kind of say, like, if there is no more input for us to accept, then we've reached either a valid state because we're actually at the end of a valid email address, or we've reached a state where we're in the middle of reading a string and there's just nothing left. So I've read, but I've never found an @ symbol. I should reject that as an email address because that's not going to be a valid email address. So I'm going to pop over here to my tablet and then to kind of remind you about what the structure of this was from last class. We've got these three major internal states for our state machine that are accepting the three different parts of email addresses. We've got that local part, and what we described this as in class was this is going to be everything that comes before the @ symbol, and this is going to be just all lowercase letters. That's what we're accepting as input here. This is not truly a way to validate email addresses, but this is what we're doing with that. Then we've got the @ state. This represents that we have consumed that @ symbol from the middle. And then after that, we've got the domain part. And the domain part is going to consist of at least one letter of input or the dot symbol. This is not exactly a good state machine to parse email addresses because we can have domains now that are things like the letter A and then dot, 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 and then the end of a string. And we would consider that to be a valid email address with that state machine. But building a comprehensive state machine, as we saw, is that big. It's bigger than we can reasonably represent. This is a good enough starting point for what we want here. The thing that I want to include now is I want to add this new symbol to my state machine to represent the idea that we have no more input. And the way that I'm going to represent that we have no more input here is for the case where we're at the end of the domain part. We've been spinning around in this state for the domain part because we keep accepting or we keep consuming symbols, the lowercase letters A through Z or the dot symbol, and then we get to the end of a string. There's nothing left for us to consume. We're at the length of the string in terms of the symbols that we've got. The way that I'm going to represent that here is with this symbol. I'm going to say that this represents the end of the string. There's nothing left for me to represent. There's nothing left for me to consume. So if I have nothing left for me to consume, I'm going to move to that ending state that is the accepting. This is a valid email address state. In all other cases, so in this everything else case, I'm going to be including that end of string notation. This kind of represents I have like any other character here, or the string is empty. And so I'm not going to keep drawing that same symbol in every other place. That asterisk that just represents everything else with the other states transitions that we've got here. It includes like we're out of symbols here. We've got nothing left to consume. I think you've maybe seen that symbol in comp 2080 question mark? No? To represent something like the empty set. Some of you are nodding, some of you are looking quizzically, and lots of people are just looking at their screens doing something else. Actually, very few people. Actually, appreciate that. Thank you. You may have seen this in Comp 2080. You may have seen this in Comp 2140. You might have seen this in other math courses to represent null, basically. Like there's nothing left for us to work with. So that's that. The other thing that I want to include here is we've got these two end states. So we've actually done this already. We've got a valid and an invalid ending state. And then the last thing I want to add here is I want to make sure that we have this idea that all states really can go to this empty state or to this end state that is invalid when we have everything else from this. So I want to kind of comprehensively capture all the possible things that we could have as input. I'll come to you in just a second. And so what I really want to say here is that for all of these other cases, and I'm just going to draw red lines to this end state. For all of these, and all of these red lines, I want you to just make an assumption that all the red lines are going to have this same asterisk attached to them. To say like everything else, anything that I can't specifically match with the transitions that I've labeled here, anything else goes to this end state that is the invalid state. Yeah. For the red line to make sense, we have to check the green line first. What we were doing last time was we're going to match the most specific thing we can and then go more broadly after that. So to your question, yeah, we have to match the green line first. That has a higher priority in the matching order than the red line would have. Can you repeat that, please? The convention actually normally would be not to even represent these other states. We would just reject the input. I just want to be explicit about rejecting the input here. Yeah. Yeah.
Is this just the case where you're doing if else? Like if you have to start state in between A to Z character and go to the next stage else.
Yeah, exactly. So in our C implementation, the structure of the local part here, it was a loop. It wasn't just a conditional statement. It was a loop that basically had us checking: is this A through Z, or is it A through Z? Just keep looping until you find something that's not A through Z, and then when you find something that is either not A through Z, check to see if it's the @ symbol or not, and then choose to go from some transition from there. You can have special cases that are like in the start state, it's the empty string. I'm just going to go to the error state. We're kind of handling the start state, at least in the implementation that we had with the local part function. Any other questions about this? Okay, all right, awesome. The very last thing I want to say about this is kind of stepping through the idea of how this functions, like what it does. And really all I want to say about this is that if we were to run code that represents this state machine, we're going to be working through some input one state at a time to move through each of these different states. So given an input that looks like this one, where we have walter@example.org, the kind of procedure that we're going to go through to validate this email address is really to like start at the first symbol and then consume some symbol from this. Consuming this symbol takes us from the start state into the local part. In this case, consuming the next n characters here are going to have us stay in this local part. We're just going to keep looping through the same state while we're matching these symbols. Our next state of @ here is going to take us to the at part here. Once we're in this state, we're going to then transition with the E to our domain part. All of this is going to be matched by the kind of loop structure in the local part. And then at that point, we have nothing left. And so we take this null transition to our end state to say this is the end of a valid email address. So our state machine here is consuming inputs. It is consuming them one at a time, but we've got this loop structure that's kind of consuming as many as it can until it's not able to consume anymore. All right, okay. This is a big mess of arrows that are all colored. I hope the color coding helps a little bit in terms of like making sure that we have some sense of what these different lines are doing and what they represent. But at this point, I want to move on to take a look at Markov chains. A Markov chain and Markov models in general, this is kind of a classification of different types of models that we can have that represent these things that are called processes. Processes are kind of like an idea that we've got where we're going to move through a bunch of different states, but the movement between the states is not really represented by consuming inputs. This is something that happens as part of the model itself. Markov chains and other related Markov models are statistical models. So what they're really representing is the likelihood of moving between states. And what we're going to build up to represent this looks a lot like a state machine, where we're going to have states and transitions between those states to represent different kinds of outputs. Markov chains and state machines, like I said, they really do look quite similar. If you squint at these things, other than the colors showing up here, the overall structure that we have between these two different kinds of things looks very, very similar to each other. With a Markov chain, we're going to have a set of states S, where the set of states are responsible for emitting symbols. This is different from state machines in that our states in a state machine don't really represent symbols at all. They represent kind of like a state of operation based upon us having consumed input. The edges that we have in the state machine that's on the left side here, these are consuming digits, 0 or 1, to move between the states that we've got here. With the states that we have on the right side with our Markov chain, these states are going to be responsible for emitting symbols. In this case, I'm going to say that the E labeled symbol, it would print out the letter E. The A labeled symbol, it would print out the letter A in this case. We've got a set of states S, and the states themselves emit symbols. Markov chains generate output. Where a state machine is consuming input to move between states, a Markov chain and Markov models are generating output. They are printing things. They're producing outputs. The outputs that a Markov chain produces is a statistical similar thing to the things that it's been trained on. We'll think about that in a moment. But the outputs that it generates are statistically similar to the things that this Markov chain was originally trained on in the first place. But the primary difference between state machines and Markov chains here is that Markov chains, they spit things out. They generate stuff. A state machine will consume symbols. Markov chains don't technically have a start state. They don't technically start anywhere, but we're going to have a start state so that we can start from somewhere. We're going to have a start state so that we can start from somewhere. Markov chains would typically not have any kind of start state at all. They would just have the set of states that have transitions between them that represent the likelihood of moving from one state to another. So we've got the set of states S that emit symbols. They're printing stuff out. They're generating outputs. We're going to add a start state to the Markov chain that we're building. And then we've got transitions between states. and these represent the probabilities of moving from one state to another. In the model that we have here on the right, the Markov chain that we've got, from the state E, there are two different transitions that we can make. One of them is a self loop back to E, and the other one is a connection to A. The sum of these values that we have is going to be equal to 1 because these are likelihoods that we're going to transition from one to the other. I have to transition out of the state. There's a 100% chance that I transition out of the state. 30% of the time I'm going to transition to E, 70% of the time I'm going to transition to A. When we're generating output with Markov chains, we're going to use random numbers. We're going to use random numbers to make decisions about which state to move to as we're proceeding through this chain. What I want to do for us is I want us to be given some training data, some data that represents the kind of output that we want our Markov chain to be able to produce. And I want to be able to go through the process of dynamically constructing a Markov chain and its probabilities from the training data that we've got. The way that we're going to do this is we're going to have input data. The input data are going to be words. When I'm using the word words here, what I mean is these are going to be sequences of symbols. Symbols, at least with email addresses, are the atomic idea of the letters A through Z. We've got characters here. The symbols that I'm thinking about here are going to be a little bit more complicated than that. But as we step through these words, we're going to add the two symbols that we have that we're looking at right now. We're going to slide our way across it. We're going to add these two symbols if they're not already in the Markov chain. We're going to add an edge. The edge is going to be directed between those two symbols, and that's really going to say we've observed a transition from this symbol to this symbol. We have seen this thing. That's what our edge is going to represent here. We're going to initialize it with a score of 0 if it doesn't already exist. And then in all cases, we're going to increment that. We're going to add 1 to this. We're going to say that the probability now of moving from this state to this state is going to change slightly. We're going to increment this edge. I would like us in class now to build a Markov chain that will be trained on sandwich data because, oh my gosh, I am so delighted to be able to do this with you because this is something that I feel like I've helped a tiny bit with. My partner is a grade 7 teacher, and she's teaching students in grade 7 a little bit about how large language models work. And I tricked her into teaching grade 7 students about Markov chains. And so all these 12-year-olds are like going around talking about this idea, and they don't have any idea that they're talking about Markov chains. But I'm telling you, we're going to talk about Markov chains, but we're doing fundamentally the same thing. Her approach doesn't actually involve doing the training that we're going to do, to be clear, but the underlying mechanism that she's talking about with that is the same as what we're doing here. So what I want to do is I want to spend some time building up our Markov chain here with the training data that we've got. So I'm going to put the training data to the side here, and I'm going to have my tablet open. And what I want to do with this is I want to start taking the training data set that we've got and using that to build up this Markov chain. For the training data that we've got here, the words, a word is a sandwich. A word is a sequence of symbols. The symbols that we have for our sandwiches are like the parts that we have in the sandwich. So the symbol that we have on our first piece of training data here, the first symbol for the first sandwich is bread. The second symbol for the first sandwich is peanut butter. The third symbol is jam. The fourth symbol is now bread. Our word here is a PB&J sandwich. This is a peanut butter and jam sandwich that we've got. That's the word that we have for this thing that we're training right now. In our Markov chain, we are going to have a starting state. And I'm going to draw that the same as I did with our state machines. Our first piece of training data, I'm going to write this out shorthand. So B is for bread. We're going to have peanut butter and not lead. We're going to have jam, and then we're going to have bread again. The first two states that we are making observations about here are the one that's just to the left of the first symbol, which doesn't exist, but it's the starting state. So our first two symbols that we're going to consider with this are going to be the thing that's before this that I'm going to label as S. And the first transition that we'd want to make is to the state that's going to emit bread as a symbol. So I'm going to draw the start state here. We've got that added. And we're going to now add the state that is bread. We're going to add an edge that's directed between those two states. We're going to initialize this edge to 0 to start, and then we're going to increment it. I've observed this happening once. I have one outgoing edge from my start state to bread, and this happens 100% of the time. So far, every case that I've ever seen will go from start state to bread. Bread is always going to be the first thing that I have in my sandwich. I'm going to move then to the next two symbols that we have in this word. So now we're looking at bread and peanut butter. I want to add bread to the state to this Markov chain if it doesn't exist already. It does, so I don't need to add it. But I do want to add peanut butter. This is a new state that I want to add to this Markov chain. And I want to add a transition between these two states. It's going to be directed. I'm going to initialize it to 0. And then I'm going to increment it by 1. 100% of the time so far, with the training data that I've observed at this point, I go from start to bread, and then I go from bread to peanut butter. 100% of the time. That's the only kind of sandwich that we've ever seen so far. So 100% of the time, we're going to make that transition. Then I'm going to take a look at the next pair of symbols in my words. Here I've got peanut butter and jam. It's the same general approach. Peanut butter is already there, and I'm going to add jam to this. I'm going to add a directed edge between these two symbols. I'm going to initialize it to 0. I'm going to increment it to 1. 100% of the time, I've seen peanut butter and then jam. And the very last symbol pair that I have here is jam and bread. Jam is already there. Bread is already there. And so I'm really just going to add an edge between them. Initialize it to 0. And then increment it. This is a terrible Markov chain because it's always just going to generate peanut butter and jam sandwiches. No matter what random number we choose as a transition between the states that we've got, it's always going to generate peanut butter and jam. So I want to move to my next training data. We're going to add now, we've got this start state that's implied. We've got bread, we've got peanut butter, and then we've got bread. So somebody doesn't like to have jam on their peanut butter sandwiches. I don't know why I picked jam, because in my family we don't really have peanut butter and jam sandwiches. We have peanut butter and honey sandwiches, but not peanut butter and jam sandwiches. But I don't know, yeah, thumbs up, thank you, yes, thumbs up. I don't know why I decided to put jam in here, but that's just where my brain went. Okay. Our next training data is bread, peanut butter, bread. We're going to have this implicit start state at the beginning so that we have some transition to begin with. We're going to look at the first pair of symbols in our words. That represents that we go from the start state to bread. What I'm going to do is I'm going to increment this in two ways. I'm going to increment that. We have seen now not just 100% of the time we go from bread. It's still 100% of the time we go from start state to bread. But what I'm actually going to say here is that out of the 2 times that I observed this transition from the start state to bread, twice I have gone from the start state to bread. Still 100% of the time, but now we have it represented as a fraction here. Our next pair of words, SI and symbols, our next pair of symbols is bread to peanut butter. Same deal, bread and peanut butter already exist in this Markov chain. I'm going to increment this edge, and I'm going to do the same thing here. I'm going to say that out of the 2 times that we've made this transition, both times we went from bread to peanut butter. And now we've got this new transition here that goes from peanut butter to bread. We don't have an edge that's directed from peanut butter to bread yet. And we only have one edge that goes from peanut butter to jam. So I need to add a new directed edge between these 2 states. I need to go here from peanut butter to bread. The outgoing edges that we have from this need to add up to 1, and we need to increment this change that we've taken, or this transition that we've taken. So I'm going to initialize this to 0 to start. I'm adding this edge initially. I'm going to initialize it to 0. But now what I want to be able to say here is that I'm taking this and I'm seeing it once, but I've seen 2 total transitions coming out of peanut butter. Half the time with the training data that I've seen, I went from peanut butter to jam, and half the time I went from peanut butter back to bread again. I'm going to keep training our model here. So that's our first 2 training sets. I'm going to write out the rest on my screen here. So we've got bread. Whoops, sorry. We've got bread to peanut butter to peanut butter to peanut butter to bread. So this is like extra, extra, extra peanut butter on the sandwich. We've got bread and ham and bread. And then we've got bread and ham and cheese and then bread again. So let's keep training this. For the next one, we've got the start state. We're going from the start state to bread. We're going to not add anything. We're really just going to make changes to the likelihood that we've made observations about here. So after our third training set, 3 out of 3 times, sandwiches start with bread. The next symbol that we've got there is bread to peanut butter. Here. So we're going to add 1 to the existing edge that we've got here, this one. And what we're going to say here is that we're going to increment, We're going to increment both the numerator and the denominator that we've got here to say that going from bread to peanut butter, again, this is 100% of the time we've made this observation. Yeah. I'm going to talk about stop states in a moment. Right now, I just want to focus on training the model that we've got. Stop states are going to be a little bit different with what we're doing with Markov chains because we're using this to generate output as opposed to accepting some kind of input. There's no real accept state in what we've got that says this is valid or invalid. We're going to use stop conditions to make decisions about when to stop generating output from our training model. But that's a good observation to make. Are there any other questions before I just keep going on this mind-numbing training exercise? Yeah.
So this, in the process of kind of generating stuff, it never accepts input or doesn't make any decisions other than the probability that it has from current state?
All we're doing is really trying to represent the likelihood of moving from one state to another based on the things that we've seen. So we're not accepting these inputs. We're just assuming that all the data that we get really represents something that that can be representable by this set of data that we've got.
So like this is so the only thing that decides how it's going to function are those probabilities, no other decision making.
There's no other decision making here. It's only the probabilities that we're going to use to make decisions about how to go from one place to the next. Yeah. Yeah.
So you said we initialize them to 0?
Yeah.
Like an implementation detail, or what is?
That's something that I would say would be an implementation detail. Like as you're starting to write code for this, choosing 0 as a starting value for your edge weights is a good choice.
It's so valuable for us to like think about initializing 0 just for like designing this on paper and stuff like that.
What I'm going to show you after this is a strategy for doing the same kind of thing as we're doing here, but with matrices. When I say matrices, I mean two-dimensional arrays to represent all the connections that you have between these things. And then using 0 for two-dimensional matrices as a default value kind of makes the whole exercise a lot easier to represent. Yeah. Yeah.
So like about the use cases of this kind of Markov chain, are we using it only for generating stuff?
For us in this course, we're only going to use it for generating things. As statistical models, these are used for other purposes, and there are extensions to Markov chains that I will make mention of, but are out of scope for this course. The one I'll make mention of right now is called a hidden Markov model, where here we're just saying that bread is going to be emitted by this state. Hidden Markov models, there's not just probabilities of moving between states, but there's probabilities that you've emitted a symbol from a state. These are used in the field that I have a background in called bioinformatics to do things like doing gene prediction. So trying to recognize where in a DNA sequence a gene starts and stops is a good use of a hidden Markov model to do stuff like that. But that's kind of outside of scope of this
So
course.
the states that we have are always going to be what it generates, not something like an action on.
Yeah, this is always going to generate, the bread state will always generate a piece of bread. The cheese and ham and peanut butter states will always generate peanut butter and ham and cheese. They won't make choices about what to generate, they'll just generate that thing from the state they're in. Okay, so we just did the bread to peanut butter transition. Now what I want to do is add the peanut butter to peanut butter transition. We're going to do the same thing here as we've done already. We don't have an edge between peanut butter and peanut butter. The only two outgoing edges that we've got are from peanut butter to bread and from peanut butter to jam. But what I'm going to say here is we're going to have a self loop. We're going to add this self loop at peanut butter. We'll initialize this to 0 to start. And what we're really saying is that so far, we've seen this 0 out of 2 times. But now I want to increment both my numerator and denominator here. I'm going to increment my numerator and denominator in all cases because I want to make sure that all the outgoing edges from this state sum up to 1 in total. Now what this is saying at this point is that from the peanut butter state, 30% of the time, we've gone from peanut butter back to bread. 30% of the time, we go from peanut butter to jam. And 30% of the time, we just stay in the peanut butter state. Yeah.
Kind of looking like the denominator of like any specific state we're looking at, the denominator is going to be the amount of times we've seen that state in our training data?
Pretty much, yeah. The denominator is going to effectively look like the number of times that we've seen that state. Not necessarily. If I were in a hypothetical situation of making a sandwich that goes from bread to peanut butter, and then I just didn't put the bottom piece of bread on, so like I just slapped the peanut butter on the table, then I'm not going to add any output edges from peanut butter. So there would be no additional transition here going from peanut butter to counter. It would just be like I stopped at peanut butter here.
Only if there's an outgoing arrow?
Only if there's an outgoing arrow, yes. So what we're counting here in the model ultimately is the outgoing arrows that we have from those states. So if we were to go through and count the number of times that we see bread in the training data, we're only going to have half as many of the outgoing edges because there are only half as many outgoing edges there. Yeah. Okay, so peanut butter again. Peanut butter to peanut butter transition was happening once. We're going to add peanut butter to peanut butter transition here again. We're going to do that same thing. What we're going to do is increment our denominator in all cases. We've now seen this outgoing thing happen 4 total times. But now, half of the time, we've seen peanut butter after itself. A quarter of the time, we went from peanut butter to jam, and a quarter of the time, we went from peanut butter back to bread. And then this very last transition that we've got here is from peanut butter to bread. So we do the same sort of exercise. We're trying to leave the peanut butter state. And we're going to increment this transition from peanut butter to bread. So 2/5 of the time we're going from peanut butter to bread. 2/5 of the time we're going to stay in the peanut butter state. And 1/5 of the time we're going to generate a jam sandwich on top of our peanut butter. Okay, now we're going to add ham sandwiches to this. Now I want to add ham sandwiches to this. We're going to do the same sort of exercise here, but I'm just going to rapid fire through this. I'm not going to try to dwell on this too much. We're going to do this start state to bread transition 100% of the time. We're going to have bread as the starting point for this sandwich. We now have a new state that we're adding to this, which is the ham state. Gosh, I want to go to these states. We're going to add this ham state. We're going to move from the bread state to the ham state. We're going to initialize this to 0, but what we're really trying to say here now is going to be that 1 out of 4 times we're going from bread to ham, and 3 out of 4 times we're going to peanut butter. Then we're looking at ham back to bread. So what we're going to make observations about here is that to go from bread back to ham, we've got 1 out of 1 time that we've left this ham state, we're going to the bread state. So 100% of the time after ham, we've got bread again. And then we'll do our last training set here. So we've got bread to ham once. We've got 1 more time from starting state to bread. So this is 5 out of 5 times we go from the starting state to bread. We're going to increase the total number of times that we've left the bread state. And now we're going to say that 2/5 of the time we're going from bread to ham, and 3/5 of the time we're going from bread to peanut butter. Now we've got a transition from ham to cheese. We've added cheese here. We're going to add this edge, and we're going to say now that a half of the time that we've got ham, we went to cheese, and half of the time we went to bread again. And then the final transition that we've got here is from cheese all the way over to bread again. And 100% of the time that we've seen cheese, we've made this transition back to the bread state. So at this point, what we've got is a trained Markov chain. We've got a trained Markov chain here that represents the 5 total sandwiches that we've seen. Yeah.
The transition from cheese should be back to ham and then to bread.
You're right. Thank you. this should go here. Thank you. So 1 at a one time, we leave cheese and we go to ham. And then what we're going to say is from the ham state, 2/3 of the time that we leave the ham state, we're going to go to bread. Thank you for catching that. Yeah. Yeah.
Just for like avoiding confusion, could you also change the data set diagram from bread to ham to cheese to ham to bread? Is that what we're talking about?
When I was doing the yes, thank you. Let's be consistent with what I've got on the screen here. There. So now we're consistent. Yeah. Okay. So at this point, what we've got is a trained data set that represents all of the different kind of sandwiches that we're able to make in this system. I'm going to go back to the slides here. And I want to describe this idea to you very briefly. I want to visualize this idea to you, but we can also represent this graph structure that we have as matrices. The way that we're going to model these transitions as matrices is going to have a matrix that represents the numerator of all of the probabilities that we've got, and a matrix that represents the denominator for all the probabilities that we've got to go from one edge to the other. The numerator transition matrix, I'm going to call it T sub n, and the denominator one is going to be T sub d. The idea here is that I want to take the set of symbols that I've got, and I want to make a couple of n by n matrices that represent all of the transitions that we have between these different states. So I'm going to move this up just a little bit here. And really what I mean by that is, in the training data that we've got 5 total different states that represent outputs, and we have 1 state that represents our start state. So in the matrix that I would want to build here, I'm going to have entries for my start state. I'm going to have entries for bread. I'm going to have entries for peanut butter. I'm going to have entries for jam. I'm going to have entries for ham. And I'm going to have entries for cheese. I'm going to write C here for cheese. So B, peanut butter, jam, ham, and cheese. Okay, so we've got 2 matrices here. One of them is going to be our numerator matrix, and the other one is going to be our denominator matrix. For every element in both of these, we're going to initialize them to zeros. Nope. This is just like watching paint dry. But I'm grateful that it's faster with copying and pasting. Yeah. We're going to initialize all of these to zeros. Every element that we have in each of these matrices is going to represent the likelihood of moving from one state to the next state. That means that we're going to have things that are looking a little bit like this state here. This state here represents the likelihood, and in combination, I guess, with this state here, this represents the likelihood of going from peanut butter to bread. That's what I want to represent with these ideas. We're going to initialize them all to 0. Then for every pair of symbols that we have in each word, I'm going to increment an entire row in my denominator matrix. So what we did with our visualization of this state machine was to go through all the denominators and add 1 to them. That's effectively what I want to do here. So if I were to see this transition from the start state to bread, what I'm going to say is I want to initialize the entire row that I've got here, increment the entire row that I've got here to 1. So I'm changing just the denominators here, but at this point I'm still really saying the likelihood of going to all those states is 0 because the numerators are all still 0. Once I've incremented that entire row, I'm going to increment just the one transition that I'm actually making this observation about in the numerator matrix. So I'm making the observation that I'm going from the start state to bread, so I'm going to initialize or increment just this. I'm going to just do this one. I'm going to erase this so that it's actually visible for what we're doing here. So this is 1. And then for our denominator array, what we've got is these are all going to be 1 now. And I'm not going to redo this entire training exercise because, oh my gosh, that's going to be real painful for me to do that. But I think you can see where I'm going with this. As I've got this training data set, I'm going to go through each one of those things and increment both the denominator matrix and also just the one element in the numerator matrix. And really what I'm trying to represent with these two matrices is going to be all of the edges that I've got between these different states. I'm going to pause here for a moment. Just making sense, everybody? Okay. All right, awesome. Once we've got our models, and I'm just going to put a little note here. This is incomplete. Exercise for the reader to fill it in. Yeah.
Whenever we increment the matrix numerator even one time, the entire row of the denominator all goes up. Right?
The entire row of the entire row of the denominator, yes, has to go up by 1. And we're trying to make sure that we have a sum for all of the possible outgoing edges from this state to be equal to 1 in total. We have to have 100% probability of leaving this state. Yeah.
I just wonder, in a way, is it then like redundant to have an entire matrix to represent all 1s and they're all going to change at the same time in the denominator, or at least kind of
Is it redundant? Yeah, I guess it's redundant, but it sure makes it a lot easier to reason about. I'm not going for optimal space consumption. I'm also not going for optimal time consumption here. I'm just trying to make it easy for us to reason about it when we're thinking about it. If you wanted to have this just be that you have, I'm going to erase like all of these. If I were to do this basically, it would be functionally equivalent to it, yes. I'm going to undo that, but like I said, I really just want us to be able to reason about this. And at least for me, it's easy to reason about this if my matrices are the same size. Yeah. Is that what your question was about? Okay. Okay, all right. So we've trained our matrices, we've trained our model. The next thing is to try and use this model to generate output. The way that we're going to generate output from these models is to use random numbers to make decisions about what the symbol is that we're going to emit from this model. The structure of this is that we're going to start at the starting state. The starting state here is going to be that solid dot that we've got in our state diagram. We're always going to start at this starting state in our Markov chain. And from there, what we're going to do is generate a random number to decide which path to take, to decide which transition to make from this model. So the structure that we've got here is that we've got our start state. We've got our start state. And I'm going to zoom in on my model here so that we can see just the model. The state that we're in right now is that we're on the start state. And what I want to do is make a decision about which state to go to based on some random number that I'm going to generate. I'm going to generate a random number here. It is 93. 100% of the time we go from the start state to bread. So that's the transition that we're going to take. If I'm generating some new output here, the very first thing I'm going to generate is going to be that we've got bread as an output. That's our first output from this model. Once we're in the bread state, we've got two possible states that we can transition to. 3/5 of the time, we're going to go to peanut butter, and 2/5 of the time, we're going to go to ham. So really, the way that we can represent this is I can say anything that's 60 or below is going to be that I'm going to go to the peanut butter state. Anything that's 60 or higher, I'm going to go to the ham state. So I got 70. 70. Yeah, 70. I've got 70 here. So 70, I'm saying that I'm going to take the ham transition now. So from bread, I'm going to go and I'm going to emit ham from this. From the ham state, we've got two possible transitions that we can make. We've got the transition to cheese, that's 30% of the time, and we've got the transition to bread, back to bread, that's 60% of the time. I'm going to generate some random numbers. We're going to say that the first transition goes up to 30%, and then 30 and higher is going to be back to bread. And so I'm going to say that I've got 35 here, so that's higher than 30. So we're going to generate bread for the next thing in our model. From the bread state, we can go to several different places. We can go to the peanut butter state and we can go to the ham state. I'm not going to count that, it fell on the floor. We've got 31 here. So 60% of the time we're saying we're going to peanut butter. So our next state is to go to peanut butter. Once we're in the peanut butter state, we have several different transitions we can make. We can go to jam, we can stay in peanut butter, or we could go back to bread. 1/5 of the time, so I'm going to say anything that's 20 or less, I'm going to go to jam. Anything that is then 80 or less, between 20 and 80, I'm going to go to 20 and 60, I'm going to go to peanut butter, and then between 60 and 100, I'm going to go back to bread. We've got 34, so we're going to go to the peanut butter state again. This is a statistically likely sandwich to be generated by this system. This is a terrible sandwich. This is a really, really awful sandwich, but it's statistically likely to come out of the model that we've got. To your question earlier of where are our final states, we're going to go until we have some end condition. And I'm going to zoom out of this now. I want to do this like constantly. I just want to keep generating output from this model until some end condition is met. There isn't going to be an ending state here formally. All of them are going to be likely at some way, shape, or form to become my end state. But I want to stop generating output from this model once I've got an end condition. End conditions can be anything like the total number of states visited. So I only want to emit 30 symbols from this. So I'm just going to spin through this until I've emitted 30 symbols. Or I only want to generate things from this until I've met conditions like I've visited this state this total number of times. For us generating sandwiches, a good ending state here would be to say things like, well, I actually just want to stop emitting output once I have 2 pieces of bread. I don't want to keep generating more output because it's just going to lead to terrible sandwiches as I start mixing ham and cheese and peanut butter and jam together. So realistically, what I'd want to do here is once I hit bread a second time, I'm just going to stop. I'm not going to generate any more output from this model. And if I do, I'm going to start back at the start state again to start generating more output from this model. With the model that we've got here, we have a start state, but you don't necessarily have to start at the start state. For us generating output here, it makes sense to start at the start state. However, we could also say, I'm going to start my sandwich with bread and I'm going to put peanut butter on it. Now tell me what to generate. If I'm going to say stuff like that, I'm going to say I'm starting in the peanut butter state and I'm making decisions about what to generate next for this sandwich. So while we have this starting state for us, for this example, we're starting at the start state, but you can just as likely start anywhere else if you want to. You can choose a state in this model to start from. Yeah.
When you say we want to control some decisions at the beginning, does that mean we're going to change the way our Markov chain flows, or is there like some kind of manual override? I guess we can leave it like that, but still make those decisions.
So I guess what I'm saying is, like, if I want to start from an arbitrary location in this model, that's fine. So if I'm choosing I'm externally making a decision. I want to start with, I've already got bread and peanut butter. Tell me what to get next. I'm kind of just saying into my own head, I guess, I've already seen bread and peanut butter, but I'm now currently in the peanut butter state. That's the last symbol that was emitted from the model that I've got that represents sandwiches. But this is just me saying, this is the state that I'm starting in now. Please generate the subsequent outputs for me from this thing.
Separate from the Markov chain, we can just structure our whatever our object. We can manually put the bread.
Yeah.
Okay.
I can kind of say something like, I have an initial sequence of things that I have already. Please tell me the rest of what this thing looks like. Fill in the blanks after this. Yeah.
Making it like learn from what it has generated, or is it going to brain kind of?
So that's a really good question. The question is it worth training the model based on what it's generated? Training the model based on what it's generated would technically just lead to the same distribution that you have now, because the thing that was generated from this ultimately was generated by those statistical likelihoods. Unless your random number generator is broken, at which point it may generate something that looks different and the likelihoods will be different. When I'm rolling dice here, this is what I would call a truly random uniform distribution of random numbers. If your random number generator generates 4 every single time, you're going to train your model so that it just takes a path always through the same thing. If your random number generator skews to the other sides, you're going to generate one of 2 paths that are the most likely. So training it based on the data that you generated is going to cause a feedback loop and really just either retrain itself on the same thing that it started with or train it on your random number generator. Yeah. Yeah. Can you repeat the question a little bit louder, please?
That's not like a equal output. That's multiple ways to sum up to one.
On these dice, no, there's not. So this one is a 100. This is a 10-sided die that has units of 10 on it. And then this is a D10 that has like 0 through 9 on it. So with the two of the dice that I've got, it should be uniformly likely to end up on any of the numbers across 0 through 100. Yeah.
You're letting them represent the digits.
I'm letting them represent the digits, yes. Yeah. I guess I should have been clear about that. Yeah, these aren't just 6-sided dice. Yeah, you could use 6-sided dice, I guess, to try and represent those things. But now you're going to have problems like things that are kind of unlikely will never happen because if it's only 1/6 of the time, but 1/3 of the time, or I'm really sorry, 1/16 of the time this unlikely thing happens, you might never see that transition if you're choosing something like dice. But this is going to be out of 100 that I've got with the dice that I've got. In code, you would use a random number generator that's going to generate random numbers between 0 and 1, and then truncate it at 2 digits to get your number between, or the likelihood. Yeah.
Like, is what he just mentioned in terms of using the output as training synthetic training data, or is that different concept?
I'm not. So the question you're asking is really, if I generate output from this and use it for training, is that what would be considered synthetic data? I guess technically yes. But again, I'm going to say that with the simplistic models that we've got here, we're just going to be training the same thing back into the model from outputs that we're getting from it. Again, unless our random number generator is skewed in some way. So like if we're using D6s to do this generation of output, we might never take a path just because our random number generator never takes that path. That's now better representing how our random number generator works with this thing. Assuming it's uniformly distributed, we would just get the same kind of training data. Okay, so this is kind of silly, like making sandwiches with stuff, but this is really what Markov models do. And I wanted to share a website with you. I put this alongside today's lecture notes, not Chang. Susam Pal wrote this article. Susam has been blogging for decades at this point and has basically taken all of the blog posts that they've got and used it to train a Markov chain, Markov model and a Markov chain, but they're using trigrams. So this is like 3 subsequent letters. This is one symbol is 3 letters that they have, or three characters that they have in their blog posts. And they used that then in this Markov chain to do what we've done here, except their model is huge because it's trigrams of ASCII characters and not just 5 sandwich toppings that we could possibly have. But it generates output that when you look at it, it actually kind of, like, up until about 4 words in, looks like it makes sense. And this is ultimately the underlying model for large language models. I'm hand waving a lot here, just to be very clear, but this is what underlies large language models, in that their search space is just so much bigger than what we're able to do in a class like this. But this is getting toward that same idea. All right, so at this point, you should be able to take this idea of a state machine. You should be able to describe it. This is coming from Comp 2400. You should now be able to describe effectively how it's able to accept input and reject invalid input. So use it for validation of data. You should also be able to start to be able to describe basic AI models and algorithms like Markov chains. When we come back next week, so 1 week from today is our next lecture class. We'll spend some time talking about the last part of the project, because that's going to use Markov chains to generate output. And then we're pretty close to the end of the course. So we'll get a better idea of how things are going to look after that. That's it for today. Thank you all for sticking around, and I will see you on Thursday. Bye, everybody.